So for this class, for Thermodynamics 1, we have an introduction to vapor power cycles. We don't cover the whole chapter. There's some things that we skip, and I think a lot of students are very much interested. Professor, what do I need to read? What do I skip? Well, we're going to cover the ideal Rankine cycle. We're going to talk about thermal efficiency, some metrics. How well does that system perform? We typically measure the performance using thermal efficiency. That makes sense. We also will be introduced to the back work ratio. How much energy that comes out of the turbine has to go back to feed the pump to make the system work. And we'll also just look at specific work out, like how many kilograms have to go in a loop for every kilojoule of work produced. That's another metric. So 3 metrics we look at. We then go back and we revisit from the end of chapter 5, the Carnot cycle. There is a Carnot vapor power cycle. And when we do that, that gives us kind of the gold standard, the benchmark by which to measure the ideal Rankine cycle. And we'll finish that out today. We'll talk a little bit as opportunity affords to increase the pressure of the boiler, decrease the condenser pressure, how that improves performance and why, and then how we can add superheat. Reheat is not here this semester. No, skip reheat. It shouldn't be in the list. And then we can add irreversibilities into certain locations, typically in the compressor. Not the compressor, I'm sorry. The pump and the turbine. We can add irreversibilities and redo the calculations. Irreversibilities in the turbine, irreversibilities in the pump will only degrade the performance of the system. It won't enhance it. But that's the reality of this real friction in the system. And then I'd like to, if time permits, talk about the electricity that's in this room. Where does it come from? And coal-fired plants and nuclear power plants are the 2 big ones that use the vapor power cycle, where you're boiling water, condensing water, you're passing the steam through a steam turbine, and that's important. These probably more for Thermo 2. I'm not going to talk about concentrating solar power plant and geothermal power plant, but they can and often are built on the same Rankine cycle. Sometimes they change the fluid, the working fluid. They don't use water. They'll use actually a refrigerant. No regeneration, no feed water heaters, no steam traps, no cogeneration, no exergy, no exergetic analysis or efficiencies, no thermoeconomics. Okay, ready to jump into it? So this person, William John Rankine was a professor at a university, Glasgow University, and was an engineer, physicist, and these are the years that he lived at that sweet spot, really, when the Industrial Revolution is taking off and people are learning, oh, we can burn things to turn things. The steam engine's already out, right? And he did a lot of work, but one of the areas he worked in was in studying steam engines. He produced in 1859 a manual, he calls it. It would be a book on steam engines and prime movers, moving things, lifting things, turning things. That's the purpose of a steam engine. And so he's honored with his name attached to this cycle, this steam cycle, this power cycle. Well, how does the cycle operate? Well, you have 4 major components. You can just put boxes for the components. It's often easier. Or you can shape the boxes to replicate or make it look like, oh, that looks like a pump. Make it round like actually a physical pump. But you don't have to. So the 4 main components are a boiler. And then you have a turbine. It's a steam turbine because we're going to often work with water as the working fluid. And then you have a condenser. And then you have a pump. It's good to sometimes just commit to memory the list of things like, oh, ideal Rankine cycle has a boiler, a turbine, a condenser, a pump. The fluid flows out of the boiler and over to the turbine. The fluid that flows out of the boiler, we'll call that state 1. We'll talk about the pressure, P1, That's the pressure of the steam leaving the boiler, the temperature of the steam leaving the boiler, the enthalpy of the steam leaving the boiler. So we'll talk about all the properties of T1, P1, H1, S1. Those are very important properties for the energy analysis. But that's also what's coming into the turbine. What comes out, I'm stating almost the obvious, right? What comes out of the boiler goes into the turbine. Sometimes I'll talk about the turbine inlet. Sometimes I'll talk about the boiler output. What comes out, it's the same. Then out of the steam turbine and goes into the condenser, it'll be at a different state, a different temperature. T2, different pressure. P2, a different enthalpy. H2, different entropy. S2. Then it goes into the condenser. Comes out of the condenser at state 3. Again, P3, T3, all those properties, we will be interested in calculating them at state 3, and then out of the pump and into the boiler. So there's 4 states, 4 components, and then 4 states of the steam between the components. Okay. What we're very much interested in is calculating some sort of metrics for how the system operates. The 3 metrics that are important are how much work net is produced by the cycle, or you can think of the power developed, net power out of the cycle, per mass flow rate of the fluid going through each of the components in a loop. This would be the mass flow rate. Practically, you would like to not have to move a many kilograms of steam in a loop to get some power out. That's a practical, pragmatic metric. So it's also W net divided by M, or sometimes we'll use a lowercase w net, the specific work per unit mass. That's the net work out of the cycle per unit mass. Where is the work being developed in this cycle? It's coming out of the turbine. But we could put cap W dot for the power coming out of the turbine, or we could put lowercase w t, subscript t for turbine, and what would the lowercase w indicate for that turbine? It's specific power per unit mass flow rate, or power per unit mass flow rate, or specific work. It's how much kilojoules of shaft work come out of that turbine per kilogram of steam that went through. So the units on that are kilojoules per kilogram. How many times have we analyzed turbines in the previous chapter in the study of entropy, as well as in the previous chapter studying with the first law for open systems? A lot. There's nothing new. We're just now going to put the turbine into a cycle, and we'll apply the same tools to analyze that turbine. Okay, another metric is going to be the thermal efficiency. What's the symbol? Eta. What was the ratio? Something that you desire over something that had to be required to make the system work. What do we desire for this ideal Rankine cycle? We desire a lot of work out. So we desire a large W net, don't we? But what makes it work? What do you have to feed it to make it work? You have to feed it heat. Now, I forgot 2 things. I forgot one thing about this work net right up here. Let me go back to work net. Work net, is it just what goes out of the turbine, or do I have to consider what goes back to feed the pump? And so the work net is the difference between what's out of the turbine and what has to go back to feed the pump. Now notice, in the previous chapters, we said for any control volume, let's say analyze the pump, we're going to say Q in and W out. But what did we just do right here for the pump? We said we know the work's in. I don't want to talk about a negative work of the pump. I'm going to show you the direction of the work. It's an arrow on my illustration. It's into the pump, and now I'm going to always talk about a positive work into the pump. So when I calculate the work net of the cycle, what do I have to put right there? A negative sign. I'm kind of, as an engineer, I take responsibility for my negative sign. And so yes, there's a deviation from the standard traditional form of the first law for generic control volume, and we put a negative sign in front of a positive work of the pump. Okay, well, what about the boiler? That has QB. We could draw a Q dot B, that's a rate at which heat is transferred into the boiler, divided by the mass flow rate through the boiler. Or we could just talk about the specific heat transfer in the boiler, lowercase qb. Does lowercase qb have the same units as lowercase wt? Does it have the units of kilojoule per kilogram? It does. Have you analyzed heat exchangers in the previous chapter, boilers? Yes, just like we analyzed pumps in the previous chapters. We're just putting the pump, putting the boiler, putting the turbine and the condenser into a cycle. So here we're going to have QC, lowercase qc, going out of the condenser. Notice this is shown to go out. That's a positive heat transfer out of the fluid that's passing through the condenser. So the thermal efficiency, it's what we desire over what it costs to run the system. What do we have to provide? What is costing us to run the system? It's called QB. Professor, is QB the same as QNet? No. What's the same as QNet? WNet is the same as QNet, yes or no? It's a cycle. And the net heat in is equal to the net work out. That's always true. So this is definitely true. Don't forget it. But in here, we're going to have WT as positive minus WP because that's back into the cycle. And over here for QNet, we're going to have QB into the boiler minus QC, what is thrown away out of the cycle. So there's two negative signs in that equation. One in front of the work boiler, the work of the pump, and the other is Q of the condenser. So don't put here an error. Don't put QNet. Because if you did, you'd calculate the efficiencies 100%. Okay, so that's a metric of the performance. The other is called the back work ratio. What's a back work ratio? Abbreviated BWR, just lowercase BWR. Back work ratio. Well, you just don't want the pump to take a lot of what the turbine produces. So you would like a small back work ratio. You would like to have the pump not be taking a large percentage of what the turbine produces. That's called the back work ratio. So for these metrics, for WNet, let's say this is a simple metric, you would like that to be high. You like this metric to be high. You'd like, for every kilogram that went in a loop, you'd like a lot of net work out. How about for the thermal efficiency? What would you like for the thermal efficiency? Would you like it high? Would you like a lot of work out for the heat that was into the boiler? Yeah, we would like a high. How about the back work ratio? You want a large back work ratio? So sometimes our metrics flip on us and like, no, I want a small back work ratio. That's what I like. I don't want a large back work ratio. I want a small back work ratio. So the job then is to go through and analyze and get the states here, find out what is the temperature, the pressure, the enthalpy, the entropy, then using the information in each of the states, calculate what are the values of the Q's and the values of the W's of the four components, and then calculate the metrics. The three metrics are easy. There's probably more metrics that we can talk about. Let's just focus on this as an introduction. So here is an illustration, cleaned up. Do I have the boiler? Do I have the turbine? Do I have the condenser? Do I have the pump? Did I put the state 1 the same place, state 2, state 3, and state 4? Let's talk a little bit about what would naturally come out for the condenser. For the ideal Rankine cycle, ideal means everything's reversible. No irreversibility, no entropy generation, no friction, okay? But what would logically come out of the condenser? What can you describe? How would you like to, what would come out of the condenser? If it's a good condenser, it's going to come out liquid. What came in? Some steam. There was some heat transfer to cool it off, and it condensed. So what logically comes out? Saturated liquid. All right, that's a perfect thing to feed the pump. Remember, we analyzed the difference between a compressor and a pump, and you really like to feed liquids into pumps. Kind of the high end of a liquid is not a subcooled liquid, but a saturated liquid. Now, what can come out of a boiler? Well, superheated steam. But what would be the lowest of the quality or the superheated steam would have that it would be saturated vapor? It would be on that cusp. It's kind of the minimum superheated steam. It's the saturated vapor that's coming out. If you heated it up some more, it would become superheated steam. That's good. We will analyze power plants where they have superheated steam. But often you peg state 1 to be saturated vapor and state 3 to be saturated liquid. Let me ask this. There are Qs for each of these 4 devices: the turbine, the condenser, the pump, and the boiler. The Qs, okay, these are the heat transfers, right? 2 of these devices definitely have non-zero heat transfers. Which are the 2 devices that have non-zero, and are any of the other devices have 0 heat transfer in our typical analysis of these devices? The turbine. The typical analysis of the turbine is that the turbine has no heat transfer. It's a well-insulated turbine. Likewise, for the pump, typical analysis, it's 0. Now, let's analyze QC as shown right here for the condenser. What would be a first law analysis around the condenser? It's operating steady state, neglect changes in kinetic and potential energy. Tell me, what is lowercase qc from a first law analysis of the condenser? It'll be the H2 minus H3. It'll be the change in the enthalpy of the fluid flowing through. Where did we see that? All the way back in chapter 4 or whatever. It was the first time we did the first law analysis. Yeah, there's a few steps in there, but I don't want to go back to the most generic form of the first law and apply it and strike all those terms and convince you of that. But there it is. Does it make sense? It comes in with more enthalpy, higher enthalpy at state 2. There's a heat transfer out of it, energy transfer out of the fluid in the condenser, and it goes out with a lower enthalpy at state 3. So if I wanted to calculate this, it's H2 minus H3. How about in the boiler? First law. What is the direction of QB? Into the fluid, into the boiler. What would QB be in terms of changes in enthalpy? It'll be H1 minus H4. H1 minus H4. So we want to get the enthalpies at these states. That's the key property. Let's talk about the work for each of those devices. 2 of those devices have no work. Which 2 devices have no shaft in or out of them? Yeah, the boiler and the condenser have no work. We do a first law analysis around the turbine, noting the direction of WT is out of the turbine. And what is WT? It's going to be a difference in enthalpies. It's going to be H what minus H what for the turbine? H1 minus H2. Now, you got to go slow for the pump, just like you had to go a little slower for the condenser. The pump, does it add work to the fluid? Does it add energy content to the fluid? Which H is higher? Is H4 for the pump greater than H3 because of the pump? Sure. And so the work of the pump is H4 minus H3, is it not? If I got those enthalpies, I could get that work of the pump. You're saying to me, Professor, we just studied the pumps. And we just studied, and we know that the work of the pump is just V dP, a good approximation. Neglect changes kinetic potential energy. It's where we left off last class. And it's incompressible, it's liquid, it's going through the pump, it's not changing. It's the first approximation. This would just be V3 times P4 minus P3. You're absolutely right. You're absolutely right. And so the way that we normally calculate H4 is that we take H3 and we add WP, where we calculate WP as VDP. That may sound like Greek to those that haven't been studying thermodynamics intensely for the last few weeks, but it should be music to your ears at this point. Like, oh yeah, that makes sense, sure. Some of the pieces of the puzzle are falling together. What are the three big metrics? Specific work. That is going to be the work net out per kilogram of flow in the loop. We would like that to be as high as possible. Thermal efficiency, we just talked about it, uses the Greek symbol eta. It's going to be the net work per QB, what comes into the cycle. It only comes in the boiler. We want that as high as possible. The back work ratio, yeah, we have to go back and feed some of that beautiful mechanical shaft power back to the pump. And what's it going to come at? It's going to reduce the net work out of the cycle, which drives electric generator, which then makes electricity typically, and then we sell that electricity and make money. That's where this power cycle is often used, to generate electricity and make money by selling the electricity. Well, to help us understand this, we want to put this on one of the property diagrams that we've been studying. What are the two property diagrams that we've studied intensely so far? The PV and the TS. The TS is the one, just to let you know, you can do it on a PV, but I don't want to take the time to put it on a PV and a TS. But I'm saying the TS is the one that really helps us on this one. So on a TS, is there a dome? Because we're taking water, we're boiling it, condensing it, boosting it through a pump. Yeah, so we're going to put a dome here on the TS diagram. And right away, you need to put 4 states on this TS diagram. And some of the keys to help you figure out the 4 states is to think about the pressures, the temperature, whether it's superheated, subcooled, saturated vapors, saturated liquid, that type of information to help you. So there's 2 devices in this cycle that change the pressure. And then 2 devices where the inlet pressure and the outlet pressure are approximately the same. What 2 devices do not change the pressure of the fluid flowing through them? What 2 devices, they have the same inlet and outlet pressure? That's a key observation. Okay, let's talk about the turbine. Think about the pressure inlet to the turbine and the pressure outlet of the turbine. From your experience, is the pressure inlet the same? Or is it higher than the outlet? Or is it lower than the outlet? The pressure. The pressure of the turbine is traditionally much higher on the inlet than the outlet. Okay, so it's not the turbine that I'm looking for. What am I looking for? The boiler and the condenser. The turbine, pressure drop. The pump, pressure gain. But the pressure 3 and the pressure 2 are the same. So basically, if I cut this system in half, that's a cut in half. What is this side? Is it the high pressure side or the low pressure side? This is the high pressure, P high. And what is this side? P low. So the boiler operates at 1 pressure, the high pressure, the boiler pressure. The condenser operates at 1 pressure, it's the low pressure, it's the condenser pressure. So right away, if I could put 2 lines of constant pressure on my TS diagram, one at the boiler pressure, one at the condenser pressure, then I know that my 4 states, 2 of them lay on one of those lines and 2 on the other line. What does the line of constant pressure look like on a TS diagram? That's right. So we go like this. I'm going to kick it over, up, come across, and then go up. And that's going to be P high. And then another line of constant pressure, go like this, go across, it come up, and that's P low. Did I do that correctly? And it's hopefully very important that you get this so that you could do it with a blank sheet of paper. And in your mind, you work through problems on the exam and stuff. It's like, oh yeah, this helps me organize the information. Now we have a lot better chance of locating state 1, then 2, then 3, then 4. Where is state 1 on this diagram? It's at high pressure, saturated vapor, right? So where is that 1? Right there. I'm going to pause. I'm going to walk around the room. I want you to fill in the other states. I want you to fill in the other states on the TS diagram. Oh boy. All right, let's pick it up here. We've done second law analysis, first law analysis of turbines. True? If you have a reversible, no entropy generated in the turbine, and we said the turbine's insulated, the Q of the turbine is 0, what do we know about one of the properties? One of those properties that you know from thermodynamics is constant through the turbine. What is that property? Enthalpy? Is the inlet enthalpy equal to the exit enthalpy of the turbine? No. What property for a reversible adiabatic turbine? It's isentropic expansion of the steam through the turbine. So S out of the turbine is equal to S in. That's why we like the TS diagram. The TS diagram helps us model exactly what's going on with the second law. And in the second law analysis of that turbine, S2 is equal to S1. True? So where is state 2 on a TS diagram? We know it's on that lower pressure line, straight down. And a lot of people are kicking it over some way, one way or the other. It's straight down. That's state 2. What happens to state 2 if there's not the ideal turbine, not the reversible expansion of the steam through the turbine, but there was actually some irreversibility, some entropy generation? It would be kicking it out to the right, and it would stay on that low pressure line. You just have higher exit entropy coming out. Okay. Now, what comes out of the condenser, state 3? Where is state 3? Some people are stopping state 3 right there. Is that the place to stop state 3? Where is the place to stop? Way over there. It's at that saturated liquid low pressure. Now the hard one. We've forgotten already, just like we needed to use the second law for the understanding of the performance of the turbine, you need the second law for understanding the performance of the pump. Where is state 4? Straight up. A lot of people are putting state 4 where? Is that where state 4 is? No. And last time I even said we exaggerate the difference between the spacing difference between the blue and the red line down in this state 3, state 4, and often it's less than 0.5 degree C temperature change between the two. Very small, but we'll exaggerate it on illustrations like this. But those lines are very close together. State 3 and state 4 are almost on top of each other. Almost on top of each other. True? All right. So that's a helpful diagram because now we have a graphic tool to help us go through and evaluate these states. And when you evaluate these states, I encourage you to put them on a table, put them in a table. So let me click through to the next one where I basically have already put on the TS diagram. And I just typed in what is the Q0. These are the delta H's in terms of the states, H2, etc. Again, this is my TS diagram. Do you see what I did? I included it. I know it's miniaturized, hard to see maybe, but can you see it? Is there some value to it? What is this red line right here? Line of high pressure. We would call that the boiler or condenser pressure. Which one? The boiler pressure. This is the low pressure. That's the condenser pressure. Pressure at 2 is equal to pressure at 3. 2 and 3. Sometimes that's why we try to organize. Put 1 here, it kind of lands in the upper right. Put state 2 here, the lower right. Put state 3 here, the lower left. And then, that's why we lay it out that way, to hopefully map it onto the TS diagram nicely. All right, so I need to find information and get these enthalpies because that's the key. So for state 1, I like to organize a table and make a column. Pressure, temperature, quality, some specific volume, it's sometimes not needed. Enthalpy, always needed. Entropy, almost always needed. So, typical problem is you're given the pressure at 1. What is that? The boiler pressure. What other pressure, if you're given pressure at 1, there's another pressure at either state 2, 3, or 4 that you now know. Which one is it? Pressure boiler. These are the same pressures. How about if I give you the condenser pressure, the pressure of the condenser? That's state 2, but it's also the same as state 3. There's only 2 pressures in the ideal Rankine cycle. Okay. How about the temperatures? Somebody says, I've given you the boiler pressure. Can you give me T1? How would you find T1? So it's the saturation temperature, Tsat, at P1. So you give me the boiler pressure, and you tell me it's saturated vapor coming out of the boiler. I know the temperature of the steam coming out. Do I also know the quality of the steam coming out? X. What is the quality at state 1? 1. What is the specific volume and the enthalpy and the S? V sub G, H of G, S of G, isn't it? Okay. So really, I like to add an extra little column, and it's like either how I describe or how I fix the state. What are the 2 key pieces of information typically given in the problem like this? Basically, they give me the pressure of the boiler, and they tell me that it's saturated vapor. That's all I needed. The pressure and its saturated vapor, I got the rest. I get the temperature, I get V sub F, V sub G, H of G, S of G. I've got it all. Now, let's go down to state 2. Where is state 2? It's at the exit of the turbine. What's happening going from 1 to 2? It's going through the turbine. The TS diagram helps emphasize what's happening through the turbine. One property is constant. Is pressure constant? No. Is temperature constant? No. Is enthalpy constant? No. It's this brand new property. To you it's brand new, but it's been around since the 1850s. Entropy is constant. It's isentropic expansion for the ideal Rankine. So really, one property I can tell right away in this whole list is which property? S2 is equal to S1. This is the same value of entropy. Then I think, if I know the condenser pressure and I'm able to do a second law analysis of the turbine and infer the entropy, the game's up. I've got them all now. I got 2 independent intensive properties. I can get the H. I can get whatever, temperature. True? Now, just looking at it, How would you describe the condition of state 2? Superheated, subcooled liquid, saturated vapor, saturated liquid, two-phase liquid vapor mixture. Well, how do you describe the condition of state 2? It's two-phase. So guess what's not going to, this quality is going to come in between 0 and 1. If this was drawn to scale, can you estimate the quality at state 2? Just visually, could you estimate it on this TS diagram? It's the length of this line divided by the length of that line, right? And so it looks like 85%, 90%, maybe that high. Are you thinking 85 to 90%, somewhere in there? Yeah. So visually, this number should be determined. There's going to be a TS diagram on the next slide that's actually real data for water. And so the length of the lines do work as a visual measure of the quality. So how would I actually physically calculate the quality at state 2 knowing entropy and pressure? We recall that the S at state 2 is equal to S of F plus the quality of state 2, S of G minus S of F. Is that a good equation? Sure, that's how you calculate the properties, just like enthalpy, specific volume, internal energy, and entropy in that two-phase region. So you just calculate X2 is equal to S2 minus S of F divided by S of G minus S of F, where those saturated liquid, saturated vapor entropies are based on that condenser pressure. Once I have the quality at 2, then I can get H2, can I not? How would you calculate H2? The H of F plus the quality at 2 times H of G minus H of F. All right. So that's H2. If you wanted, you get V2 as well. You really don't need V2 for most of it. What about the temperature at 2? T2. How do I calculate T2 if I need it? It's what? Saturation at the pressure P2, which is the condenser pressure. Any questions about state 2? How about state 3 now? What fixes state 3? Pressure and it's saturated liquid. Once they tell me, oh, this is the condenser pressure and it's saturated liquid, game's up. I got it. So what is the temperature at state 3, T3? It's Tsat at P3, and that's the same pressure as P2. Are these two temperatures the same? Hold, it went through a heat exchanger. It went through a condenser. There's a lot of heat transfer out of that steam. You're telling me that the temperature inlet of the steam and the temperature outlet of the steam in the condenser is the same? There was a change of phase. It was constant pressure condensation, condensing it. And yes, this is one of these incredible things. I'm afraid that a lot of students will learn that in Thermo 1, maybe forget it, they relearn it in Thermo 2, but by the time they get to senior design, they forgot it. For the rest of their life, they forgot it. They don't know. They don't know. If I'm going to transfer heat out of a fluid, the temperature of the fluid's going to go down. No, you can transfer heat out of the fluid and the temperature of the fluid stay the same as long as you're condensing. True? That's what we're doing here. Please don't leave this class without that. And I'm not teaching Thermo 2 for a long time. So if you don't get it this one, and I don't know who's teaching Thermo 2, but you know, get it. It's good to know these things, right? All right. So now what about the quality at state 3? 0. What about the V of state 3? That's V sub F at that lower pressure, the condenser pressure. Then it's H of F at that condenser pressure and H of G at the condenser pressure. True? Now what about 4? Well, just like 3 and 4, it's on a straight line up. So what do we know about the property at state 4? Which property can I tell in addition to pressure at 4? That S4 is equal to S3. Why did I write H there? This is SG, okay? So it's the same entropy, but that's usually not the way we do it in hand calculations on the exam. On the exam, we say it's reversible. You're going to neglect changing the specific volume of the water going through it because it's considered incompressible. And so what we do is we typically calculate the work of the pump is VDP, P4 minus P3. I just repeated myself, right? And so if I wanted to get the enthalpy at state 4, you would just take the enthalpy at state 3 and add the specific work of the pump. Usually you don't go and play with the entropies to get state 4. Okay? This is the enthalpy at state 3, the H of 3. This is S4. Is S of, F, sorry. I wrote both things wrong, didn't I? I wrote H of F, and then I tried to fix it to write S of F, and then I wrote S of G. Anyway, thank you for fixing that. Good. Okay, so that's typically what you want, because you really want these enthalpies, because once you got the enthalpies, you got the Q's and the W's, and then you can calculate the backwork ratio and thermal efficiency of the cycle. So, recommendation, use a table to organize property information. Use a table to organize information about the Q's and W's for your devices. And then remember your metrics. Use a property diagram as well. Well, here's a real problem. So they say, ideal Rankine vapor power cycle operates with steam as the working fluid. Saturated vapor enters the turbine at 7 megapascal. Once they say something like that, guess what they just give you in the 7 megapascal? That's the pressure of the boiler. That's all 7 megapascal. That's the steam that comes into the turbine. The condenser pressure is 10 kilopascal. Determine that you have a bunch of these. Get the work of the turbine, the condenser heat transfer, the pump work, the boiler heat transfer, the thermal efficiency of the cycle, and the backwork ratio. Before we get bogged out on that, this is a real temperature entropy diagram plotted with the assistance of the NIST program RefProp. So where can we put the states? Well, we're at 7 megapascal, saturated vapor. Can you see where it goes? Isn't it 7 megapascal right there? Isn't it? And then, where is the 10 kilopascal? Well, this is 0.1 megapascal. That's 100 kilopascal. This is 0.01 megapascal. Is that 10 kilopascal, this pressure line right here? 10 kilopascal. Okay. So we're on this pressure line right here. Where is state 2? Straight down. There's state 2. There's state 1. Now where is state 3? And where is state 4? It's so close, it's incredible, I can't hardly show it, but there it is. Same entropy, a half a degree C higher. All right. If I get and go zoom in and zoom in, yes, using the tool RefProp, I will see the difference in the two lines. But at this perspective, at this zoom out, you can't see it. So look at this. What's visually the quality at state 2 off of this diagram? Give me your visual estimate of the quality at state 2. 75? Okay, 75%. The quality at state 2 is about 75%. And let me do this. What approximately is the temperature at state 2? Temperature at state 2. 40-ish? Just 40-ish, right? That's 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. It looks like it's around 40-ish degrees C. Okay. Let's do this. What is roughly the temperature at state 4? Around 40.5 degrees C. It's just wild guessing. I mean, you have to really zoom in. Well, think about this just for a minute. What is the temperature of the water coming into the boiler? What temperature? Around 40.5, 40 degrees C. What is the temperature of the steam coming out of the boiler? Way up here, right? Just draw across close to 300. Not only does it get hot, changing from 40 to 300, but it greatly expands because it goes in liquid and goes out saturated vapor. It greatly expands in the boiler. True? All right. Okay. Now, let's just slug through this problem. This is our TS diagram to help us. The illustration with all the states, a little reminders, saturated vapor, saturated liquid. So we would put right here for kilopascal, we put 7. Is that 7 megapascal is 7,000 kilo? Did I get that right? And this temperature, we visually saw it was around 300. You look it up, 286 degrees C. And the saturated vapor, you can get the specific volume, you get the enthalpy. Enthalpy comes 2773, and entropy is 5.8146. What about, just a reminder, what two things helped us fix it? The pressure, and it was saturated vapor, or quality. You could say quality is 1. Let's take a look at the next line. State 2. Well, 5.8146. And what's the pressure? 10 kilopascal. Knowing the pressure and the entropy, knowing that it's two-phase, you can go and get the quality. The quality is going to be around 0.69, 0.689, somewhere in there. About 70%. We're pretty good. We estimated 75 just looking at the graph. Using that quality, you can get the H. It's going to be 1839. A lot lower. True? Okay. What is the pressure at state 3? And then what is the other piece of information for state 3? It's pressure in a saturated liquid. Quality is 0. This H is 192-ish. And entropy is 0.6492. So you could see the enthalpy, a dramatic reduction, as well as the entropy. Can you see that the entropy really did drop a lot on the diagram? Okay. And then what about state 4? Well, for state 4, what I would do is I would go and I'd calculate the specific work of the pump. That specific volume of state 3 times the pressure 4 minus the pressure 3. The specific volume of the liquid at state 3 is around 0.000, no, it's too many zeros, 0.001010 meter cubed per kilogram. and the pressure for 7,000 minus the pressure 310, all kilopascal. And I do my favorite unit conversion. What's a kilopascal times a meter cubed? What's a kilopascal times a meter cubed? Kilojoule. So we can calculate to get the kilojoule per kilogram specific work of the pump. And you do that, and it comes in, the specific work of the pump is around 7.06, very small, kilojoules per kilogram. And so now what is H of 4? Well, really just nice to put it in the table. We really don't need it because we calculated what we really needed, work of the pump. But you add that 7.06 to 192 and you come up with 199. I know that there's some extra digits out there, but I'm just rounding off to 3. You would include more digits in your table, okay? Yes, sir.
I know you said it earlier in the class, but why is the pump there?
Why is the pump what?
Why is the pump needed in that system? Just because it doesn't really do much.
No, it doesn't. It boosts the pressure. Yeah. But what you're probably getting at is the net work out is approximately the same as the what comes out of the turbine, because there's very little that goes back to feed the pump. You're absolutely true. And a lot of people will just say, forget the pump. The net work out is what comes out of the turbine. That's true. What that means is you have a very low back work ratio, which is good. Does that make sense?
So if I took the pump out?
Well, first of all, you can't take the pump out of the cycle because how am I going to get the pressure up? I could take the pump out of the energy calculations or energy balance calculations as long as it's as long as it's a low back work ratio. Does that help or not? Okay. So we basically get all of these H's. Now it's easy. Because what's the work of the turbine? The work of the turbine, H1 minus H2. Do I need to memorize that, Professor? No, you need to be able to rederive it just by looking at the diagram. It's coming in at high enthalpy, going out low enthalpy. The purpose of the turbine is convert as much of that flow enthalpy into shaft work. That's what it is, first law. Okay, and the second law really limits it. The second law says this H2 just can't be anything. This H2, the best you can do is 1839 for this problem. If there would be some irreversibilities, the entropy here would be like 5.9 or 6.0 or 6.1. And as that entropy drifts up, what do you think that enthalpy is going to do? Drift up. The enthalpy difference across the turbine goes down, less work out. How about the condenser heat transfer? Q condenser comes in high, enthalpy state 2, minus the enthalpy exit state 3. And you calculate it. For this problem, the work of the turbine came in at 933 kilojoules per kilogram. The heat out of the condenser is 1647 kilojoules per kilogram. A lot of people will look at this 1647, look at 933 and say, what a wasteful system. Here it is, 933 going out where I want it to go, but 1647, a lot larger number, going out wasted, just dumping it to the atmosphere. Terrible. You engineers need to do better. But guess what this is? It's the ideal Rankine. This is pretty good. There's no friction in the turbine. Wait till you add friction in the turbine. Gets worse. All right. So let's keep going. What about the work of the pump? Hey, we just calculated the work of the pump, didn't we? 7.06. So WP. Now here is where the net work is 933 minus 7. Somebody said, it's close enough to 933. No, it's going to be the 926. 926. You have to subtract the 7 off. Okay, Let's continue on. What's the boiler heat transfer? QB, that's big. That's 2574. There's a lot of heat. A lot of kilojoules for every kilogram going through that boiler. What about QNet and WorkNet? We just calculated them. They're going to be 926. What is the thermal efficiency then? Well, it's 926. That's the work net out divided by Q boiler, 2574. The efficiency of the cycle comes in at 36%. That's a pretty good efficiency. We can do better. Actual power plants are running better, but they don't stop the boiler at saturated vapor. They superheat it. They superheat the vapor. That's better for the performance of the system. And then what's the backwork ratio? Well, we calculate the backwork ratio as the ratio of the work that goes back to feed the pump divided by the work that came out of the turbine, and we find it to be 0.8%. Not 8%, 0.8, less than 1%. Right? So that's nice, that's good. It's low. We like a low backwork ratio. Can you solve a problem like this on your own? Well, what we want to do is we want to contrast the ideal Rankine cycle with the Carnot vapor power cycle. Yeah, this guy, Sadi Carnot, French engineer who wrote this document at a young age and then died. He died at 36 years old. In 1824 he issued it, and we still talk about him today. So what would be a Carnot vapor power cycle, and how would the ideal Rankine compare? You see this word ideal. What did it mean on the Rankine cycle? No friction in the turbine, no friction in the pump. The best turbine you can imagine and the best pump. That sounds like that's a pretty good system. But the question is, and it's hard to grapple with, is it just as good? Are both of these just as good? Is the Carnot vapor power cycle, which has no friction in the turbine, no friction in the pump either, is it just as good, or is it a little better or a little worse than the ideal Rankine cycle? Same boiler pressure, same condenser pressure. Trying to compare apples and apples and oranges, not get them mixed up. But would they be the same? Let me go back and review what the Carnot is. So we already know what the ideal Rankine looks like. What four components? Boiler, turbine, condenser, pump, and the Carnot has exactly the same four components. And the fluid flow from the boiler to the turbine, we'll call it state 1 in the Carnot, just like it was state 1 in the Rankine. From turbine to condenser, state 2, same. State 3, same. State 4, same. But there's going to be a difference. There has to be a difference. We're going to take saturated vapor out of the boiler. That's the same. But what about state 3? This was saturated liquid. No. In order to have a Carnot cycle, state 4 has to be saturated liquid. What? State 4 has to be saturated liquid. Well, let's do this. Let's understand the difference by sketching and comparing the temperature entropy diagram. Here's the temperature entropy for the Rankine cycle, true? Now let's put up the same dome. Let's put the same high pressure line and the same low pressure line. The high pressure is the pressure of the boiler, the low pressure, pressure of the condenser. We're state 1 on the TS for the Carnot. This is Carnot now. Did it change location? State 1 is the same. How about state 2? Did it change location, or is it the same location straight down? No, it's maximally efficient. Just like the turbine, for both of them, the turbines are no entropy generation. It's isentropic expansion of the steam through the turbines. Now, where is state 3 and where is state 4? So state 4 now is the easier one to find, isn't it? State 4 is saturated liquid at the high pressure. Where is state 4 on the diagram? Right where a lot of you were putting it in the Rankine cycle. I think you were reading and getting them a little mixed up, right? And then, where is state 3? Straight down below. Is state 3 saturated liquid? Nope. So state 3 has some quality. It's a two-phase mixture, but there's state 3. And you look at it and you say, same components, but what do we have on the TS diagram for the Carnot? How does it compare on the TS diagram for the Rankine? It's a box. It's a box on the Carnot, and it's not a box, is it? So where's the big difference? And if you understand and observe why they are different, then you'll see why the efficiency of the Carnot cycle, where you have same working fluid, same boiler pressure, same condenser pressure, you have same state 1, same state 2. So what goes out of the boiler into the steam turbine is the same in both cycles. And there's no reversibility. No irreversibilities in the turbines or in the pump, okay? But they're different in performance. You'll find that thermal efficiency of the Carnot is better than the ideal Rankine thermal efficiency. Why? It's a very subtle point. But if you... I'm sorry? It's in this, what's happening over here on this side. And a lot of people, when they talk about the Carnot vapor power cycle, they wouldn't even talk about this as a pump. They would say it's half pump, half compressor, because you're taking in some substance that may be, I don't know, I'm looking at it, it looks like it's about 70% liquid and about 30% vapor, right? It's a two-phase mixture, so it's taking in some liquid, some vapor. It's kind of a mixture of a pump and a compressor. That device doesn't exist. Engineers develop compressors to take in gases or vapors, and they develop pumps to take in liquids. And you never want any liquid to go into a pump. A vapor into a pump. It don't work very well. Likewise, you don't want liquids going into a compressor. Okay. So it's right there where the rub is, but somebody else give me an observation of what's different. What's different? The pressure change across that device is the same. 3 to 4 is the same. It has to do with temperatures. Has to do with temperatures. And what it is over here, we said that we exaggerate the temperature difference between 3 and 4, but 4 is really cold fluid. And when that cold fluid goes into the boiler has to supply heat, supply heat, supply heat, supply heat, and finally get it up to the point where it starts to boil. Then it boils, it's supplying heat, supplying heat, supplying heat, supplying heat. Look at over here. The second that fluid goes into the boiler and it starts to add a little heat, what happens to that fluid in the Carnot? It starts boiling right away because it's already saturated liquid. If I add a little heat, I'm going to get some vapor right away. What about the Rankine? It was cold liquid. I added heat, it just made it warmer liquid, warmer liquid, warmer liquid. It had to crawl from about 40 degrees C in the calculations that we just did up to around 390 degrees C before it started boiling. You see that? Why is this here wasteful? Why is that so bad for performance of a heat engine? Well, you go back to Clausius's inequality, and you say that we want to bring in heat, Q, And when we bring in the heat, we divide it by the temperature at which it comes in, and that's entropy coming in, right? If you bring in the same amount of heat, but you bring it in at a low temperature, can you see that you're bringing in a lot of entropy? And when you bring in this heat at low temperature, you're bringing in more entropy. Where does that entropy have to go? Oh, you can destroy entropy. Can you destroy entropy? Nope. It can only get more of it, and you don't want it. You're going to have to dispose of the entropy. You have to push it out of the system. Where are you going to dump it? You have to only dump it in the condenser. So entropy is going out down here with that heat transfer, and you're dumping out that entropy. It's like a waste product. But because you brought in the fluid into the boiler at low temperature, you're bringing in a lot more entropy as you add heat to the fluid, and that means I'm going to have to throw more out of the cycle, more heat out of the cycle. It's from an entropy perspective that you can see that it's wasteful. I did the best job I could. It'll be repeated in Thermo 2. I hope you master it in Thermo 1, and then you can yawn like you're yawning now in Thermo 2. But it is really an important concept, because one of the design strategies for real power plants is they're going to eliminate that. They're going to, before that water that's feeding the boiler, before the feed water gets to the boiler, they're going to warm it up. And it will greatly improve the efficiency of the cycle. And every power plant out there that's running, that's, serious power plant, which has been a lot of engineering design behind it, they're going to have feed water heaters and strategies for bringing that temperature up so it's not so cold when it goes into the boiler. So the efficiency of the Carnot will be better than the efficiency of the ideal Rankine. But we said that this sort of pump-turbine combination is impossible. It's not practical. It's just not a device out there. I call up, some vendors say, yeah, I'd like to buy a pump. No, I'd like to buy a compressor. No, pump, compressor. I'll tell you what, I can't decide. Send me both a pump and a compressor all together in one device. They're going to laugh at you. Yeah, I want to feed it 20% vapor and 80% liquid. They're going to say, figure out what you want to feed it. Get it all liquid or get it all vapor, but don't send us. We don't make a device like that. Okay? So this device is theoretical. This pump or turbine over here or compressor over here is theoretical. But we know that if we could build it, we would have a higher thermal efficiency for the Carnot. Let's compare this. The back work ratios, and our other metric was the work net out per mass flow rate for these two cycles. This one is the obvious one. Everybody, Carnot is going to beat out the Rankine, no problem, on the thermal efficiency. But what about the back work ratio for the Carnot and the back work ratio of the ideal Rankine? You have to have more insight, I think, to really answer that question. But think about, do you think that you're going to have to feed a lot more work to the pump in this Carnot? Probably. So this was good, having a better, higher thermal efficiency. How about the Carnot having a higher back work ratio? Bad. Terrible. And the back work ratio is significantly higher, even in this theoretical device cycle called the Carnot cycle. What about the work net? This one's, you have to almost run some numbers to see it. But the work net of the Carnot and the work net of the ideal Rankine, because so much of the turbine out of the Carnot has to go back and feed that pump, okay? And we're keeping it the same high pressure, at the same low pressure, the same boiler pressure, same condenser pressure. It's still starting from state 1 and going to state 2. It's the same 1 to 2. Hey, they look the same. The turbine produced the same amount. It's just I've got more of the turbine output going back to feed this pump. That basically the Rankine is better. So this is also bad from the perspective of the Carnot. More kilograms are going to have to flow in the Carnot per second in a loop to get the same total power out of the cycle. All right. What you do is you want to go through this cycle. The key is to get the states fixed. You make a table. You say, what fixes state 1? Pressure, and then it's saturated vapor. What fixes state 2? Low pressure and entropy. What fixes state 3? Well, think about state 4. Often it's best to go back to 4 first. It's the pressure and saturated liquid. And now go back to state 3. It's the lower pressure, the condenser pressure, and entropy. So S3 is equal to S4, just like S2 is equal to S1. If you get that diagram straight, it helps you a lot. And get a table and fix. And what are the most important? The enthalpy values. Well, here's a summary table for you. Trying to show you how you do it by hand. So the S2 is equal to S1. And for the Carnot, S3 is equal to S4. And once I get those entropies at state 2 and 3, I'll get the quality at state 2 and 3 using the entropies. Once I get the quality at state 2 and 3, then I calculate the enthalpy at state 2 and 3. That makes sense? All right. For the ideal Rankine, these two states look a lot alike, these two up here. But what's different is typically you analyze the pump. You got that VDP term for the pump, and you move from saturated liquid up to adding that much to get H4. H3 is the saturated liquid enthalpy, and then add VDP to get the compressed liquid enthalpy at state 4. I'm just repeating, summarizing what we covered. Is this table helpful? Don't forget, you just make a little table, your devices, the Q's and the W's once you have it all, and then compare that net work, thermal efficiency, back work ratio. This one here is going to be the better, the net work for the ideal Rankine. This thermal efficiency is going to be the better. The Carnot is going to be better than the Rankine. The back work ratio, the better is the ideal Rankine. Okay. Actually, a lot of people will talk about the ideal Rankine as a practical Carnot. Why? Because this device is impossible, taking that two-phase mixture and compressing it. This device is practical. What do? Just throw a little more heat away in the condenser. Easy enough to do. Bring out saturated liquid out of the condenser. It's practical Carnot. You're close to the Carnot as you can get, making it practical. And now feed it into a pump, saturated liquid. It bumps up a little bit, and there you go. Okay? For just a device, a cycle with 4 devices, there you go. All right. You should be able to do this. You should be able to say, go back, 7 megapascal boiler pressure, 10 kilopascal condenser pressure. Analyze a steam Carnot vapor power cycle. Just do that. When you do that, I've given you, summarized all the tools. You can make that comparison. And here's the comparison again. For the turbine work, we really didn't change the inlet or the outlet states of the turbine. Both of them have 933. The condenser, you're going to throw more out of the Rankine. You have to throw more out. You're going to condense the last 20% or so. The pump work is going to be a lot less for the Rankine because this has a two-phase mixture coming in. It's impossible pump. The boiler, you're going to be more heat into the Rankine, because you've got to heat it all up before you get a saturated vapor. Saturated liquid. Okay. Q net is the same as the work net for both cycles, but the work net is greater for the Rankine. This is good to have it here. This is higher. I just mentioned that. There's really a 43%, if you just run the numbers, increase in the work net, meaning that for every kilogram that makes a loop in the cycle, the net work out is 43% greater for the Rankine than the Carnot. Thermal efficiency, though, is lower. It's 16% lower. The Rankine's lower than the Carnot. And the backwork ratio, much, much, much lower. And this is very good to get a low backwork ratio. Okay, let me ask you this. You learned this equation, and I told you it's going to be on the EIT exam. Probability is high in the thermodynamics section that you're going to need to use the efficiency of the heat engine Carnot 1 minus the low temperature over the high temperature. Simple equation, true? We learned it. What is our low temperature for the cycle at which all the heat is rejected? Isn't that the condenser temperature? Add the boiler temperature. Isn't this the high? For our problem, what was our boiler temperature again? The 7 megapascal. What is the temperature high for Carnot when you had 7 megapascal? That's the temperature saturation at 7 megapascal. That comes in at 280, 5.8. What temperature is that? Degrees C? Right? And then the temperature low, the saturation temperature at 10 kilopascal, 45.8 degrees C. Do you have a calculator? Can you check that this equation gives you the same result as 30.7% efficiency? I'm sorry, not the efficiency there. 42.9%. I want you to do that. I want you to use these two temperatures. I'm going to pause, walk around, and calculate the thermal efficiency, and then compare it with this thermal efficiency that I'm highlighting right here. And do you get the same value? So we got pretty good agreement. So we actually get good agreement. You just have to remember 1 minus 45.8. And I like that when I saw somebody write it out just like that. Way to do. And then you have 285.8 plus 273. This is when I still remember the first time I did that. It's like, hold it, I did all this work. I did all these enthalpies and qualities, and I did all the calculations with the entropy, and I have all these property values, and then this very simple equation gives me the same result. Good to at least 3 digits on my calculator. I was shocked. Long time ago. I remember that. And yet it does. It gives you the same overall thermal efficiency. Professor, is there a simple equation so I can get this thermal efficiency really easily? Nah, no. Sorry. Slugged through the math. Okay. How can I improve the performance of the cycle? Go back and look again at our TS diagram. Here's our dome. Here is the line of high pressure. Where is the boiler bringing in heat? Well, we start typically low. If it's cold liquid coming into the boiler, we're adding heat, adding heat, adding heat, adding heat. Finally, we're going to boil. We add heat, add heat, add heat, add heat, add heat. You think about all of the heat brought in relatively high temperature and all this heat brought in at moderate and low temperatures. What's bad for the performance of this cycle? Bringing in heat at low temperature is bad for thermal efficiency. We want as much heat brought in as high temperature. So you're looking, and the engineers looked and they said, well, why don't I just continue to bring in some heat at that high pressure, the boiler pressure. Don't stop bringing out saturated vapor. If I stop out here, what am I going to be bringing in to the turbine? What comes out of the boiler if I stop out there? Superheated steam. So first performance enhancement, get that superheated steam. Bring it out hot. And when you expand it, then it probably won't have such a low quality on the exit of the turbine. That's also very good. You don't want water droplets on the exit of the turbine because they act like little grains of sand in the machinery. They're very dense little packets of material, and when they hit things like the blade, they can lead to erosion of the material on the turbine blade. So you want it pretty high quality. So superheat, great performance. What do you want to do? You eliminate this, so basically you're preheating. You have the feed water heaters to get it hot before it gets to the boiler. Next class. But another performance enhancement, somebody says, this is your boiler pressure, the high pressure. Guess what? Just bump it up a little. Here's a higher boiler pressure, increasing the boiler pressure boiler. Is that going to help performance? Yeah, it will. And the idea behind it is still bring in heat at high temperatures into your working fluid. So you just brought it in at higher temperatures if you bump the boiler pressure. Just the opposite. You can see it from the Carnot, but it's true for the Rankine as well. Here's my condenser pressure. Should I try to have a high condenser pressure or a low condenser pressure to improve performance? Low. You want it low. Because you want to throw out heat at this low temperature. If you want to, you have to throw away the entropy. So if I want a lot of entropy go with a small amount of Q, make TL low. It throws away a lot of entropy for the same Q. So just like if I want to bring in as little entropy as possible, make TH high. And if I want to throw out as much entropy as possible, make TL low. From entropy. How can you affect the condenser pressure? Condenser pressure. How can you affect that? You're kind of stuck. You're dumping heat to the atmosphere. How hot is it outside? You can't get colder than that. Lake water. How hot is your lake water? You can't get colder than that. Well, let's only run our power plants in Alaska. Well, that'd be great, but we got to transmit it to South Texas because that's where we need it in the summer. And so basically, no, that's not going to work. It would be more efficient. The power plant would be more efficient in Alaska because it's colder. Actually, if you work for CPS, they could see the small changes in the performance of their power plants from winter to summer. Why? Lake water temperature's colder in the winter, and they're dumping it to that lake water temperature, Calaveras and other lakes. What is the two lakes? Bronig? No. What's our two lakes that we dump it at? We have power plants in San Antonio. Bronig? And Calaveras? Calaveras is another one. You can fish on them, I believe. And you usually don't want to fish at the discharge because it's so hot, and fish don't like it because they can't get a lot of oxygen. It's hard to breathe in hot water for the fish. They like to go really deep in the summer because of the cold water and then similarly in the winter they like it at the top of the lake because it's cold in the shallows in the lake and because of the oxygen, high oxygen. Okay, so there you go, general trends for improving performance. So pump it out. Here is, if you went out here, I think I did some calculations out to 440 degrees C at that 7 megapascal. Here, compare it to the stopping at saturated. If you expand it down to the 0.01, you just increased the quality of the steam going out. That's good for performance. practical concern. So here's a quick comparison between the ideal Rankine at the same pressures, boiler and condenser pressure, but this one you superheated not to 440 to 480. Let me go back and change it to 480, so it's a little higher. Okay, then you come out. You could see that the network of the cycle is the turbine out of the turbine is improved. Q of the condenser, you're going to have to throw some more away. The pump work really is not affected. The back work ratio is affected very little, but it's small. It's really small, which is great. The boiler, Q into the boiler is higher because you're superheating it. And the net work is 32% higher, which is good. The efficiency is 7% higher, which is good. And the back work ratio is lower, 24% lower, which is good. All three were improved by superheating. I didn't cover reheat. We don't cover reheat. And if you have irreversibilities in the Rankine cycle, it drops to ideal. It's no longer ideal then if you have irreversibilities. What would it do to the turbine? Kicks it out. You have to do that two-step process going or analyzing a turbine. First isentropic, and then using the efficiency, isentropic efficiency of the turbine. Well, I didn't cover this, but maybe I'll touch on it next time. Thank you for your attention.